Vs, this is the velocity that we're going to use to measure the rate of this reaction. Because again, what we care about is the amount of product being formed per time. Now, the reason why we want to look at the initial rate of our reaction instead of looking at all the other possible slopes is that it simplifies our work quite a bit. Okay? If we think about this, right, here we start with just enzyme and substrate. We're not starting with any product. This is going to go forward until we hit ES, right? Some ES will be converted back into E and S. Some ES will also be converted into enzyme plus product, and some enzyme plus product will go back to ES, which can go back to enzyme and substrate. But if we focus only on the initial rate, which is to say the slope at t equals 0, okay, what can we say about the concentration of product at t equals 0? 0, which tells us what about this reverse reaction? Must also be 0, equal to k minus 2 times E times P. But if P is 0, this is all 0, right? So if we focus only on the initial rate, now we can ignore k minus 2. All right? Secondly, when a reaction is occurring, what we can also say is that the concentration of ES is constant. Which is to say that the rate of formation of the enzyme-substrate complex is the same as the rate of breakdown of the enzyme-substrate complex. Right? So formation of ES is equal to the breakdown of ES. These two assumptions are going to allow us to derive a very useful equation. Right? So again, we're ignoring k minus 2 because we're looking only at the initial state, and concentration of ES is constant. Okay? So, steady state assumption and the initial rate assumption. What do we do? Well, let's first look at the steady state assumption. And we'll say that the rate of breakdown of ES is equal to the rate of formation of ES. So how can ES be formed, right? Now that we're ignoring k minus 2. Well, ES can only be formed in one way, enzyme and substrate coming together, right? So the rate there is equal to k sub 1 times E times S. That's the velocity of this reaction forming ES complex. And that's the only way that we can form that. The rate of breakdown of ES, well, ES can form either E and S, or it can form E and P. Now the velocity of this direction is, of course, k minus 1 times ES. And the rate of this direction is K2 times ES, right? So let's write those down. The rate, we can add those together. So ES times K minus 1 plus ES times K2. Now we can factor out the ES and get all the concentrations on one side and all of the rate constants on the other, right? So we factor out the ES. This leaves us with times S over ES equals K2 plus K minus 1 over K1. Right? So what I've done is factor this out and move all the concentrations over here and all the rate constants over here. This ratio, right, which we can think of as breakdown over formation, right? K2, K minus 1 describing breakdown of ES, K1 describing the formation of ES. We're just going to call this Km, the Michaelis constant. Okay? Now, the Michaelis constant is different for every enzyme, right? But it never changes. It's immutable because it's just a ratio of rate constants. Okay? And these rate constants are not going to change. We can change the concentration of enzyme, we can change the concentration of substrate, right? But all we're doing is binding and breaking down. So these aren't enzyme catalyzed. This is the scheme for an enzyme catalyzed reaction, right? So here we're just talking about the binding and breaking down of enzyme, substrate, and product. So these will never change, which means that the Km for an enzyme never changes. It's immutable. It's a characteristic of that particular enzyme. Okay. Now, we can continue on here, all right? We have free enzyme concentration times free substrate concentration divided by free enzyme substrate concentration equals Km. Right? Well, let's solve for ES first, right? So let's say that ES equals E times S over Km, all right? The problem is that we don't know what E is, right? We don't know what the free enzyme concentration is. We know how much total enzyme we added to our reaction or whatever, but we don't know right now at any given moment what is the concentration of free enzyme. In other words, enzyme that is not part of an enzyme substrate complex. But what we do know is that the total amount of enzyme we added, E total, must be equal to, I'm just going to raise up this. What we do know is that the total amount of enzyme, E total, must be equal to the amount in an enzyme substrate complex plus the amount of free enzyme, because that's the only place that E can be, right? So we can rearrange it to say that free enzyme must be equal to E total minus ES. We can plug that in down here and say then that ES is equal to E, which is E total minus ES times S divided by Km, right? But now we have an ES over here and we were trying to solve for ES. So let's get that ES back over there, right? So we'll E total times S minus what do we want to say here? E S times S, right? Now let's multiply this over here. Km, and let's add. So Km ES plus ES S equals E total times S. Okay, let's factor out this ES. Right? Divide that. That leaves us with ES equals E total times S over S plus Km, right? Now, how does this relate anything to do with the velocity graph that we saw before? Well, remember, the velocity, V naught, the initial velocity of our reaction is equal to K2 times ES, right? Well, here we have ES. What if we multiply by K2, right? All right, so that gives us V naught, which means that we have to multiply K2 over here. Now we have another type of enzyme concentration here, E total, right? So what is E total times K2? Well, obviously it's going to be some kind of velocity because we're multiplying a concentration times a rate constant. But what does this velocity signify? Well, we know that V naught, the actual rate, is equal to K2 times ES, right? And this is some velocity that we're trying to figure out what it means, right? But what if we set these equal to each other? Let's say that V naught equals V whatever this is. E total equals ES. What does that imply to you? All the enzyme is used up. E total, the total amount of enzyme that we added, is equal to the amount of enzyme in an enzyme substrate complex. The enzyme is what we call saturated. All right? Now, if we add more S, there is no more enzyme to catalyze the reaction. So this is as fast as an enzyme catalyzed reaction can go. So we call this Vmax. So E total times K2 is Vmax. And here we have, again, V naught. V naught equals Vmax S over S plus Km. This is the Michaelis-Menten equation. And this tells us at any given substrate concentration, what is the concentration of, or what is the velocity of that enzyme catalyzed reaction going to be. I'm an idiot and turned off the projector, so this might take a second. All right. Pull down. Alright, so we have now our Michaelis-Menten equation. V naught equals Vmax S over S plus Km. What does this tell us about Km, right? And why is this good to know? Well, what is Km? Let's just write it more clearly up here. Again, we have V naught equals Vmax S over S plus Km. Okay, now if you take this and you plot it into your graphing calculator or on Desmos, what you get is a hyperbolic plot. We have V naught and S down here. Okay? So, what if we say that S equals Km? Right? S equals Km. What is V naught? Max over Km? Why do you think?
Because it would be Km over 2Km.
Yeah, it would be Km over 2Km.
Oh, Vmax over 2.
Vmax over 2, right? So let's say that we have our Vmax, which is equal to K2 times E total, right? Now, again, remember, we control how much enzyme we add. So Vmax can change. If we add more enzyme, that means that we have a higher E total, which means that Vmax will be higher. Regardless of that, the concentration of substrate where we are at 1/2 Vmax will always be the same. Right? So say that we add 1 millimolar enzyme to our substrate and we get a Vmax of 20 millimolar per second. Okay? And then we add more enzyme, we get a Vmax of 40 millimolar per second. And we add more, and we get 60 millimolar per second. Okay? The Vmax is changing, but we will have to add the same amount of enzyme, or the same amount of substrate rather, to get to half of whatever Vmax is under those conditions. So the Km in this case is 1 millimolar. If the Km is 1 millimolar, that means if our Vmax, after adding X amount of enzyme, right? So let's, I'm confusing it. So let's say that we have a table of E total versus Vmax, right? So let's say we add 10 millimolar, 20 millimolar, and 30 millimolar enzyme, okay? Now I'm going to make up these numbers. Say Vmax here in this case is 100 millimolar per second. Here would be 150 millimolar per second, let's say, and here, no, actually 200 millimolar per second, and here would be 300 millimolar per second. And let's also say that the Km of this enzyme is 1 millimolar. That means that we need to add 1 millimolar of substrate to get to 50% Vmax. That means that here, when we added the 10 millimolar, when we add 1 millimolar of substrate, we'll be at a reaction velocity of 50 millimolar per second. we added 20 millimolar of enzyme, our Vmax is 200 millimolar per second. We add 1 millimolar, now we're at 100 millimolar per second. So the Km is not changing. The amount of substrate that we have to add doesn't change in order to reach half of Vmax, whatever that might be, under those conditions. Okay? So when, all right, so there we go. Now, when we talk about Km, what we find is that the Km, the Michaelis constant of a given enzyme, is usually right around the physiological concentration of the substrate, right? So let's say that glucose is found normally at 5 millimolar in a cell, right? Probably close to 1 millimolar. Either way, let's say that the concentration of glucose is typically 5 millimolar in the cell. So the Km is 5 millimolar. And why is that, right? Well, now we can see if we're here, 5 millimolar. Now if there's more glucose, V0 increases, which makes sense. There's more substrate, so we want the velocity to increase. Down here, if there's less, we want the velocity to slow down because we have less glucose. So we're in this pseudo-linear range here. So having a Km that's right around the physiological concentration, the average physiological concentration gives this control over the rate of the reaction just simply based on the concentration. Now let's think of the two other extremes, right? What if the Km were, again, 5 millimolar, but the typical concentration of glucose in the cell were, say, 100 millimolar, all the way over here. Well, now we'd always be at 99%, right? We'd always be almost saturating the enzyme. So now if the amount of glucose drops, well, now we're still at 99, 98%, so we don't really get any response. And if we increase the amount of glucose, we're already saturated, so we don't get any response. So having a Km value that is much lower, right? This allows no response to the substrate concentration changes in the cell, right? If we have the other situation where 5 millimolar is the Km, but typically we find this at, say, 0.1 millimolar, right? Well, here, we're still in this pseudo-linear range, right? So we still do get to respond to changes in substrate concentration, but the rate is so low that the enzyme ceases to be effective, right? We want a decent amount of acceleration, means that we want a decent reaction velocity, and we also want to be able to respond to changes in substrate concentration. So again, what we find is that the Km value of a given enzyme is typically, you know, in the range of the average or typical physiological concentration of the substrate. All right, now finding out Vmax and Km are a little bit tricky, right? So of course we have that hyperbolic plot. Now it's easy. You can take all of your data and plot it into Excel. You still have to do some fancy math with limits and whatever to find, right, where the limit of your hyperbolic plot is. That's your Vmax. And then you have to take that Vmax, cut it in half, find where the substrate concentration intersects, and there's your Km, right, that you see over here. But finding this Vmax, right, is not trivial, right? This involves calculus and a bunch of math that I really can't keep up with. So instead, what we do is find the Lineweaver-Burke plot, okay? Now this is actually quite interesting, right? We can take our Michaelis-Menten equation, V0 equals Vmax times S over S plus Km. We take the reciprocal of both sides and just do some algebra to rearrange, right? So nothing fancy. What we come out with is that this double reciprocal equation is simply a rearrangement of the Michaelis-Menten plot. No other assumptions or anything has gone on here. You can derive it for you if you like. It's very simple. But what do we have now? We have 1 over V0 equals Km over Vmax times 1 over S plus 1 over Vmax. And what is this but a line? Y equals M X plus B. And indeed, if we plot this, 1 over V0 versus 1 over S, we do get a line. And looking at the equation, we can see that the y-intercept is 1 over Vmax here. And if we find the x-intercept, so we set 1 over V0 equal to 0 and solve, what we see is that the x-intercept is equal to negative 1 over Km. So now we take our kinematic data, right? So we find the reaction velocity of our enzyme at several different substrate concentrations. So we make a V0 versus S table. We take the reciprocal of both of those values. We plot them in Excel, okay? We plot them on a graph and fit a line, okay? And Excel has the function, of course, to fit a linear regression and show you the equation. That equation corresponds to the double reciprocal or Lineweaver-Burke equation. From there, we can calculate exactly what our Vmax is by looking at the y-intercept and what our Km is by looking at the x-intercept, right? So this is how it's typically still done, right? Just because it's easier than doing a bunch of calculations. It's definitely the way that it was done before, right? Before computers were widespread, although that seems to be longer ago than most people care to admit. All right, so Km and Kcat values are important enzyme characteristics. So Km, again, is those ratio of rate constants, and essentially, right, is the ratio of breakdown to formation, right? E times S over ES, right? E times S over ES. So essentially, we're just looking here, okay? And this is very similar to something that we've seen before. Okay? It's very similar to the dissociation constant. Km approximates the dissociation constant of the ES complex. And why is that? Right? So if we look at KD, right? In this case, we're looking at the interaction between enzyme and substrate over here, right? Enzyme plus substrate yields enzyme-substrate complex, so Ka is equal to ES over E times S, which is equal to K minus 1 over K1 over K minus 1, which means that Kd is equal to the reciprocal of this, K minus 1 over K1, right? And let's remember what the ratio of rate constants is for Km. It's K2 plus K minus 1 over K1. So we're very close to what Kd is. So how can we get these two to be equal to each other? Right? So let's say that we want Kd to be equal to Km. K minus 1 plus K2 over K1. How can we make these equal to each other? The only way that this is possible is if K2 is 0, right? Now, of course, K2 can't be 0. Otherwise, we would have no reaction, right? The velocity would always be 0. But if K2 is just much less than K minus 1, then we can say that K minus 1 plus K2 is just about the same as just saying K minus 1, right? So if K2 is much less than K minus 1, we can say that Km is close to Kd. Now, as it turns out, this is very often the case, which is why you often see Km and Kd being used somewhat interchangeably, depending on the context. If you're studying enzymology, you just refer to Km. If you're studying ligand interactions, you just refer to Kd. But functionally, most of the time, they are the same because K minus 1 is usually much greater than K2. Now, this brings us to Kcat. Kcat is a special rate constant. We haven't seen Kcat before. But what Kcat is, the definition is simply the rate-limiting rate constant, which means that it's the lowest of the 3 rate constants in our setup over here. It's the lowest of K1, K2, and K minus 1. It's the lowest. As it turns out, again, that's almost always K2, right? So Kcat doesn't have to be K2, but it almost always is, right? And Kcat and Km are, again, important characteristics of an enzyme. All right, now K2, Kcat is the turnover number of the enzyme, right? So K2, Kcat, and turnover number are all referring to the same thing, simply this rate constant over here. And it's the number of substrate molecules converted into product per second, right? Vmax reveals the turnover number. If we know the total amount of enzyme that we added, which we do because we started the whole thing, right? So if we know Kcat, we know Vmax because we can measure it. We know enzyme total because we added it. Then we can say that Kcat is always equal to Vmax over ET. The reason why we say here Kcat instead of K2 is because though, yes, somewhere over here covered by the board, we said that Vmax is equal to K2 times ET. That's just true when K2 is the rate-limiting rate constant because the overall rate of the reaction is going to be limited by the rate-limiting rate constant. So if that happens to be K1, then Vmax is not going to be K2 times E total. It's going to be K1 times E total. right? It's just easier to make that assumption that it is usually pt2, right? Especially at this level. Now, we can also use Km to find the fractional occupancy, so how many active sites are being filled. This is just a rearrangement of the Michaelis-Menten equation, right? So here, again, this should look very similar, or very familiar. This is what we found for the fractional saturation in our binding chapter, right? Instead of L over L plus KD, it's S over S plus KM, right? Again, remember, KM approximates KD, so this is functionally identical. Okay, and it so happens that this is also equal to the ratio of V naught over V max, just because it's taken from the Michaelis-Menten equation. Now, alright, K cat over Km. I'm going to finish here, okay, and then we'll get on to enzyme inhibition on Friday. So, K cat over Km is a measure of catalytic efficiency or specificity, right? So it's typically called the specificity constant. Right? And what is the true measure of enzyme efficiency? Well, we can look at equations 8 and 14 from the text, right? So I don't think anyone has those memorized, but it comes from what we've already done today. So essentially we take the fact that V naught equals K2 times ES, right? V naught equals K2 times ES, and where are we at? Over here, right? We can rearrange this line to say that ES E times S over ES equals KM, right? So we saw that from before. So we can say then that by extension ES equals E times S over Km, right? So just rearranging. What if we plug in that over here? We see that V naught, the velocity, equals K2 over Km times E times S, right? Good? So what do we have here? We have a velocity that's describing the interaction between E and S with this rate constant, right? So K2 over Km is the rate constant for the interaction between E and S, right? That's what's shown on that slide. So why does this matter? Well, if E and S interact well, okay, if E and S interact well, would we expect the rate constant to be high or low? So say we're looking here at chymotrypsin, right? So we have E is chymotrypsin and S is glycine, okay? Let's look at K cat over Km, 1.3 times 10 to the minus 1, right? So what does that tell you between the interaction of E and S, in this case chymotrypsin and glycine? It's not very strong, right? The rate constant is very small, so it's not a good interaction. But if we go down here and look at, let's say, norleucine, right, which is just a variation of leucine. Norleucine, 3.0 times 10 to the 3, right, so 3,000. Is this a good interaction or a bad interaction? Where E is chymotrypsin and S is, in this case, norleucine. It's good, right? So we have a higher degree of specificity for norleucine than we do to glycine if we're looking at chymotrypsin. So we see why K cat over Km is called the specificity constant because it's the rate constant for the interaction between E and S, right? And again, we look at the interaction between E and S, where E is chymotrypsin again, and S is phenylalanine. Well, now the rate constant is 100,000, right? So this is a very good interaction between E and S. So by knowing K cat, and we can know K cat by measuring V max and knowing how much time we started with, and knowing Km, right? We can find K2 over Km for a specific mixture of E and S and see, do they interact well or do they not interact well? Okay? All right. So we'll leave it there for today, and we will pick back up with